Okay, so today I'll just be telling you a little bit more about like some useful concepts like about like like kind of like linear algebra in infinite dimensions, which are which makes more understandable like the stuff about quantum mechanics. I tell you a little bit about that. So what I was mentioning last time is that we are considering like vector spaces, right? So you have like a vector space. Again, for most practical like for our purposes, it would be infinite dimensional. So and what I was saying last time is that we will equip the vector space with the inner product. So it has with an inner product. So for example, you like the one that we were considering last week was like the vector space, like say of periodic functions. So you consider functions, you know, I think I took the period, like, let's say period 2 pi, and I'll just to make it look nicer from negative pi to pi. Um, right, so they would be functions defined on the interval negative pi to pi, and they have to be periodic. So, for it to be periodic, really, like at the endpoints, it has to be take the same values with f of negative pi equals to f of and again, like just so that you don't have to worry about many things involving analysis, yeah, you can ask for these functions to be smooth. So f smooth. Okay, and on that vector, so that's like a vector space that's infinite dimensional. And there, like you can define the inner product, which was just like the regular integration, right? Which so if you have two periodic functions, um, we just integrate them and that will give you like a dot product. Now, in general, what I was saying last time is that just with this, this behaves more like it behaves more like the rational numbers in the sense that they're not complete, right? So like there's like like a bit of technicality because like you could have like bounded Cauchy sequences that do not converge to anything. So you have to if you wanted to kind of work properly with all this setup, you have to complete the vector space, and that gives you like the Hilbert space. But for us, I mean, like I'm kind of doing things more or less formally. So formally just means that you will ignore like all those more like subtle things about defining the domain of the operations and things like that, because that does require about a bunch of things which are more advanced, and that's called like functional analysis. But I'll just kind of like work, like kind of wink, wink, like everything kind of works fine, but really many things just go by analogy pretty well. So like I won't write anything false, but like kind of like will omit details, to not like get trapped into that. So for example, with that inner product, the next step, if you like there like you can define linear transformation. So like yeah, the you can have like a linear transformation. I'll call it let's say I'll call it like A. So for example, an example of a linear transformation, which we'll use a lot, is like the derivative, right? So well, I'll write it in a couple of ways. Like here, I just mean derivative with respect to x, or derivative. Like if you want to write it more explicitly, we just like be this like the derivative with respect to x, right? Because like a of f, right, is just like derivative with respect to x of f. And that's yes. I mean, this will, yeah, it takes like the function that's periodic, because we're assuming that everything has like smooth, you can take as many derivatives as you want. So it takes like a function that's periodic, produces like the derivative will continue to be periodic and so on. So like, that is like, the kind of like the most important transformation that we'll consider in this case. Because once you like, once you have a linear transformation, like if you think about it in finite dimensions, you can talk about the transpose of a linear transformation, right? Of a matrix, right? So what was the transpose? So that's also called the adjoint, like, so let's just, I'll call it, or, I'll call it like formal adjoint. Formal just means here that, I'm not really worrying too much about like where everything is defined, but like, if you remember, like, let's say if you had like, a matrix, like, in the finite dimensional case, if you had like a matrix, let's just say that's square, but it doesn't really matter, like, an n by n matrix. What was the transpose? Okay, yes, like, it ends up coinciding with just like the operation that swaps like columns with rows, but more like the better definition for the transpose, right? Is that A transpose, is defined by the property, that if you have two vectors, u and v, and you take the dot product of AU with V, the idea of the transpose is that you can move the matrix to the other slot, right? Like, so E, E, right? So the idea of like the, which if you prefer to write it in the dot product notation, right? This is how it would have looked, right? So like the transpose, like, or the adjoint, formal adjoint, has, that's kind of like the key defining property, like kind of like that you can move it, like it allows you to move the operator to the other side, which if you are like on Rn and are using the dot product, the Euclidean dot product, the regular one, that does coincide with like, changing columns into rows. And that is like in that special case where that gives you, but like, because we're using like a very different sort of like dot product, right? Like, or inner product, you do have to be careful like here of what that would be. So if you have but this is like kind of like the correct definition. So if you have like a vector space, yeah. So if you have like an infinite dimensional vector space, like the formal adjoint or like the transpose again of A is just that, it's given by, I'll call them F and G just to emphasize that I'll like, we'll be thinking about our example with functions. Oops. It's kind of, the definition, and then the kind of like the fun thing is to find the transpose of like, of certain operators. So like the most basic one that you want to find is the transpose of the derivative. That's the most important thing, like, most important example also for quantum mechanics. So what is, the transpose of the derivative operator, right? So again, if you think about it, like, of this taking acting on periodic functions, what you want, because of like the definition that I just gave you, is like, this is what should happen. Where here f and g are periodic functions, right? So fg periodic smooth functions. Okay. And but what does that mean? This means like the dot product, right? So the left-hand side here is just the dot product of the derivative of sorry, or like the integration, that's what I meant. The derivative of f times g of x, like from -5 to pi, right? And I mean, this will like this is what we're after, so I don't like okay, this would be like the integral from -5 to pi of f of x times like whatever this is, this is what we're trying to find the x, right? So this is what we're after. Is that making sense so far so good? Questions? But then is where you use integration by parts, right? Because like integration by parts does allow you to move the derivative to the other function, right? So if you remember, if you do integration by parts here, right? And yeah, this is just like top two, I guess. This is just f of x, g of x, right? Evaluated at -pi minus the integral from -pi to pi, and then I move the the derivative to the other side. Is that making sense? Uh, and the cool thing is that because of the periodic assumption, right, like that the functions are periodic, then this term vanishes, right? This is what people would usually call like a boundary term, because this refers to the values of the function at the endpoints, which the endpoints are the boundary of the, of the of the interval. So this goes away. Since f of pi equals f of -pi, and same for g, right? Right, so so essentially what you end up with is like this, minus this integral. Okay, but okay, let me just write it in a way that's a little bit more suggestive. I'll put it like the minus together with this factor. Right, like we can rewrite it like that, and this is just the inner product or the dot product between f and minus the derivative of g. Is that making sense so far so good? And just by comparison, right, that, so what you start, like this was fg, right? So this should be equal to dfg, right? So that means if you compare this with this, that the transpose of the derivative should be minus the derivative. So in conclusion, or this, like, because this thing gadget is precisely what the transpose or the adjoint of the derivative is supposed to do. So by comparison, is that making sense? So the adjoint or the transpose of the differentiating is just minus differentiating. In particular, that does tell you, like, so like the analog of this is kind of like that, this is the analog of a matrix satisfying A transpose equals minus A, right? That's an analog of that. So like it kind of, well, saying that this particular operation is more like skew symmetric, if you know what I mean. So this is more like, so this is kind of in a sense like skew. So the derivative is kind of like a skew symmetric or skew adjoint operation. Is that making sense? So far, so good?
So this would work kind of differently than if you did the finite case, like on the polynomials up to degree n. When you define the derivative, you can have a matrix for that, but then the transpose would look kind of different.
Okay, so that's a great question, because in that case, like, it does, finding the transpose, the way I'm introducing it does depend a lot on, like, it is very kind of sensitive to the inner product that you have, right? So you would have to think about, like, what sort of like inner product you want to use on the space of polynomials, right? Because there's kind of two ways to think about it. Like, if you have, that's where it can get all tricky, because if you have like polynomials, say polynomials of degree 2, right? So if you have polynomials of degree 2, like I think I was writing them like this, right? Okay, if you identify this with like A naught, A1, A2, right? Then one inner product would be kind of like doing the R3 inner product, right? Like the regular inner product on R3, in which case then the transpose does look more like the transpose, like down, like regular old transpose that you know, right? Because you're kind of like using the R3 inner product. Another alternative would be kind of to try to do like, this is like a polynomial. Another alternative for this would be to do like some sort of integration of polynomials, right? Like here you have to be a little bit more tricky, because polynomials are essentially defined over all of R. So maybe you would have to say, oh, just integrate from -1 to 1 or something silly like that, so that there are no convergence issues and things of that sort. But now this is like a very sort of like different, like, inner product, if you know what I mean. So depending here, like, if you were to do this for the space of polynomials, like the transpose does change, like it will look different, or it will be like a different operator depending on with respect to one inner product you are using. So, like, the thing is that in practice, you kind of think of the inner product as fixed from the beginning. So like you don't really index the transpose according to the inner product, if you know what I mean. But yeah, like depending on how you're thinking of the polynomials, then there is an inner product where it does look like a regular transpose of the derivative. Like the transpose of the derivative would just be like the regular thing. And there is another one where it would look more along those lines, if that makes sense. But but again, you do have to be more careful. Like, what sometimes happens, like when you work with functions which are not periodic, like defined on the real line, you do want kind of something like this to be more or less true with respect to the dot, like, like the integration. So you would ask like for the functions to vanish at infinity, right? Like the limit as x goes to, because then the integration by parts, like this boundary term continues to vanish. Like, if that's kind of like the main goal for this to work nicely, to get rid of this term. So one option is to do periodic functions, which is what I have been doing. But another option is kind of to work with functions that decay sufficiently rapid at plus or minus infinity, and that also would fix it. But yeah, no, it does depend a lot on how you're thinking of the space of polynomials, like, but yeah, like I guess like both could occur, like, but for us, like, because of the integration inner product, it will be more of this sort than like just like the other thing, if you know what I mean. No, but that's good. Thanks. Okay, cool. And then here's another if you okay, now let's think about what letter should I use for this? Okay, so necessarily like this notation, but when here's another thing that you would do, like in linear algebra, again in finite dimensions. Like when you have like a matrix, right? Like again, like we can think about it as being like a square for now, but you could also like, um, you doesn't have to be square. Like most matrices, square matrices are not symmetric or skew symmetric, right? kind of like relatively easy way to, like produce like a symmetric matrix out of like a arbitrary matrix, right? It's just to do kind of like the transpose, right? So that you can do like something like A transpose A, right? Like that will be automatically symmetric, right? So this one is symmetric. And I'm calling it P because it's also positive semi-definite, right? Like also positive. So meaning like, when they're symmetric, all the eigenvalues, like symmetric means like in particular because of the spectral theorem that all the eigenvalues will be real. And so in the case of positive semi-definite, it just means like, that like one of the consequences will be that all the eigenvalues are non-negative, right? So it has like non-negative eigenvalues. And so if you think about it, like, the proof was super easy, like, because you have like, what is an eigenvalue? What is an eigenvalue eigenvector for this? Is something like this, right? And then what you could do is like take P like dot product or inner product with B on both sides, right? I guess that's how the proof went. So you get B lambda B, right? But this is A transpose A, so you get B A transpose A. So that is equal to B. Oh, well, that's actually lambda, if you take it out because this is linear, like, you get the norm squared, right? And then because of the transpose properties, you can move this to the other side, so you get AB equals lambda norm of B squared, and then that's like just like the norm of AB, right? So like definitely that will force like lambda to be non-negative for sure. Right. And if you think about it, at least based on how I'm defining all these things, like this proof more or less carries through, whether like, the operator, like, like the matrix or like the linear transformation was finite dimensional or infinite dimensional, right? So like, for example, if you take something like, you know, so like, it's essentially the same proof. If you take like, if you take something like P being like that, the transpose of the derivative times the derivative, right? That will have, I mean, so of course, there's something I should say that there's kind of like a spectral theorem for like things of uh, this sort. So you can again go into the details, but still this, whenever it has eigenvalue, there will be real numbers. So essentially like the same proof will work. So if it has an eigenvalue, value, in the sense that like, P F, because now this is for functions, right? P F is lambda F, then yeah, you can show that lambda has to be greater or equal to zero. Then lambda is greater or equal to zero. And the cool thing is that you can be a little bit more precise about what P is, because what is P? P is like the transpose of the derivative. And the derivative, but we already know that the derivative is minus, sorry, that the transpose is minus the derivative, right? So you get minus the derivative, right? So it's like kind of like the minus the second derivative, right? So that's just saying, that so like minus the second derivative have positive spec or non-negative eigenvalues. And for example, if you were doing this, like with more variables, like, with X, Y, Z variables, the analog of this is to say, like in R3 or not, like, with, X, Y, Z as, with, more variables, the analog of this is that, minus the second derivative with respect to X plus the second derivative with respect to Y plus the second derivative with respect to Z. Has no negative eigenvalues, but I don't know if you have seen this one before. This is like the Laplacian, right? So what you prove here is that minus the Laplacian has like non-negative eigenvalues. So just to show you like about maybe like before I continue, let me see, are there any questions so far? Um, so let me show you how this technology gets used to trying to find some solutions to the wave equation, because it's kind of useful to go back to the PD that I had written like last time. So so let's go back to the wave equation. Okay, so back to the wave equation. And then, so again, that meant that you're trying to find a solution to this equation. For like, and you're like, again, think of U as like a function of X and T. And if you thought about it like in terms of a string, then maybe here's like the string, and like at position X from like some reference, like U of X T is just like the height of the string at time T and at position X with respect to the origin. Okay, so it's kind of like a height function for the string in this case, although like again, the wave equation does appear in there many different versions, and so there are many alternative interpretations of what U is. But then what you notice, well, like many times when you're trying to solve a partial differential equation, you kind of do like a separation of variables as a first attempt. So like try to do like a separation of variables. Which I did, I have done something very similar when I did the Hamilton-Jacobi equation, if you remember. But separation of variables just means that you will think that this function of the variables is just like a product of individual functions. So I'll call this like just, usually you will write something, let's see, what should I, okay, I'll put it like this. So we're just thinking that it depends on a function of X and a function of T. And And you know, if you think of this, like think of the string, more like you know, like a cable or like a wire that like is on a circle. So like a wheel, it's kind of like think of a wave propagating kind of on a circular string or like on a ring. So I will think of X as F as being periodic so that we can apply the technology that we have been discussing before. So here where we are assuming, we assume that F is periodic. It's just to, you know, we're not trying to solve like the equation in all generality, we're just trying to find periodic solutions to the wave equation, just to connect this to what I have been saying. So when you do the method of separation of variables, like, you know, you get 1/v², you plug this back into the equation, right? So like this would be the second derivative with respect to time of. And this is just like the second derivative with respect to x, so. Right? And now what I'll do is move all the stuff that has g to one side and the other stuff that has f to the other side. So I'll rewrite this as 1/v. V squared is just like a constant, it's just like the velocity. You could actually take it one like from now, like we wouldn't affect us too much. Like 1/g, v squared g, v squared. Equals 1/f, v squared dx squared. Right? What is the point of doing it this way? That the right hand side is, this is like a function of, like, let's emphasize like the dependency. This is like a function of x exclusively, this is like a function of t exclusively. So the only way for something that depends on x to equal something that depends on t is for each type to be itself like a constant. So all of this must be a constant. So this would be this is going to be a constant. And that constant you can call whatever you want, but I'll call it negative lambda, and you'll see why. Instead of calling it lambda, I'll just call it negative lambda for anticipation of what we just did a moment ago. So I'll just call this the constant minus lambda. Okay. So for example, if you well, sorry, I should stop. So far so good. Is that making sense up to now? So if you look just at if you look at, like, start with the like the equation that you would get for f. So for f, you would get that 1/f, the second derivative of f with respect to x is minus lambda, right? Or that the second derivative or that the minus the second derivative of f with respect to x is lambda f, right? But this, right, I mean, this is minus, you know, this is like the operator p that I defined like a second ago, right? Like the minus, I mean, it would be minus a Laplacian in 3 dimensions, but it's just minus the second derivative with respect to x, right? Right. So it's just, it is like, what I'm trying to say is that solving, you know, solving at least solving this part of the equation is just like an eigenvalue, eigenvector problem for like the minus the Laplacian or minus the second derivative. So this is like, you get to like an eigenvalue, eigenvector problem, right? Does that make sense? And because of like the things that we have been discussing, like we know first for a fact that these sources are constants to be non-negative. So that's the first thing you get for free because this p operator is like you know, it's self-adjoint, like, or like symmetric if you want, and positive semi-definite. So like that will say that, so like one of the things that you get for free that, so lambda is greater or equal to 0, right? So that's nice. And then like, okay, this is like I mean, this is like an ordinary ODE. It's not like anything too crazy, right? Like you can solve this like with ODE methods. Like the general solution is like a linear combination of sines and cosines, right? So, Oh, yeah, so like, like, and this is like, again, this is like a ordinary ODE. Is in fact kind of like, if you, relabel the variables, it is actually Hooke's law, under different guise. It is like the harmonic oscillator, actually. And so like, I mean, in the end, like, it's like an easy check to check that this is a kind of like a constant times, cosine of root of lambda x plus another constant times root of lambda x. Okay, that is, what the general solution looks like. If you just thought about this as like an ODE problem, right? Now, and again, like the comment, other, like, having called this minus lambda instead of lambda is also nice, so that here you wouldn't have to do like the square root of negative lambda. So it's kind of like another reason why it's, nicer to do it this way. Now, here, so this is what we get so far, but from like what we have been discussing, the lambdas have to be non-negative. The other thing that you get, which is more interesting, is that we are trying to find solutions which are periodic, right? So you do want to impose like a periodicity condition on the solution, right? So you do want f to be periodic. So like, if we were thinking about this as period 2 pi, right? So you want something like that. And so that does restrict, like, the values for lambda, because then lambda, like, lambda cannot be like 1/pi or something like that, because like that would mess up the periodicity. So what that forces is to lambda, so this forces, um, I mean, this forces essentially root of lambda to be like an integer. So so I mean, like that's enough, because if it were negative, like, if it's negative, you can reabsorb that into the constant. So you really can only work with like non-negative integers. So lambda is. Okay, so what that means is that, where n is 0, 1, 2, 3, 4, etc., right? Like it has to be an integer. So what that means is that from the beginning, like from the ODE itself, or like setting it up as an eigenvalue, eigenvector problem, you know that this is non-negative. But once you plus, after imposing the periodicity conditions, you do get discreteness, right? So that means that lambda, like before, like lambda could have been anything on the positive half line, or like the half line, but now lambda can only assume like discrete values, so lambda only takes. Okay. Which, depending on how anticipation of something like quantum mechanics, people would call this like some sort of quantization, in the sense that sometimes when you use the phrase quantization, just means like a quantity that ends up taking like discrete values, or like has become discretized in some way. And so this is an example of that, where like, like you can only like this, you can reduce the problem of like having like any positive number, any negative number, to just like multiples of the integers. Okay. So that, like, but let's just call this discretization. Do not. do not like confuse this with anything related to quantum mechanics because they still has nothing to do with quantum mechanics, you know. Is that making sense? So far so good. And then like the other one is like easy to, like the other part of the equation is easy to solve. Because the other like half was like that 1/g. So because now that you know the lambda has to be like n squared, you get the second derivative of g with respect to t squared is minus n squared v squared g. Okay, and again, this is kind of like a regular ODE, like you can solve it, and g of t is going to be like again like that. I'll fix like the name for the constants in a bit. But this is just like what a sine, sorry, cosine of and dt plus c4 of dt. And so just like, you know, a particular solution to the wave equation is just like a product of these two things. So like, you know, like u was like the product of these two functions. So one of them, you know, if you wanted to be more specific, like, you know, you can index it by n because you're getting one for each integer. So call this f of n, g of n, you know, that gives you one. And then you can emphasize more like the dependency of, you know, like you can emphasize more the dependency on n by just calling this like this. Okay, so it's basically determined, like, it's determined by like the factors, so it's given as a linear combination. Combination of, because again, you can play with the constants, but, how you're calling the constants, so it's cosine with cosine, so cosine of nx times cosine of nbt, and then cosine of nx with sine of nbt, and then sine of nx with cosine of nbt, and then sine of nx sine nbt. And okay, the important thing here is that, cosines and, you're essentially what I'm trying to say is that the solution looks like a combination of like things of this sort and like multiplying cosines. Like, there's like this formula for the product of two cosines, which is kind of like a linear like a sum of cosines. Where is it? I always like, for example, yeah, like there's like this formula identity with similar versions for like, there's like a similar version for all the other four, like when you multiply sines and cosines. So my point is that at the end of the day, this does generally look like a cosine of like what, nx minus nvt plus cosine of nx plus nvt. A similar thing for the others, where it's like cosines with sines and all the other stuff. So at the end of the day, the basic solution to the wave equation is literally like a cosine or a sine, right? So it is like a wave, right? Because like a cosine or a sine, if you remember the graph, it's just like, it does look, it is represented by a wave. So, so like from this perspective, yeah, like you end up getting like, so it's something like cosine of nx plus minus nvt and sine of nx plus minus nvt. So like the solution to the wave equation is kind of like, you know, a basic solution to the wave equation is given in terms of this, and then like kind of because of this Fourier principle, like you can superpose them, and because the equation is linear, so if you do like a superposition of the solutions, you continue to get a solution, and then like you know, like then that's one way to build up more general solutions to the wave equation, just by taking like kind of like a Fourier series out of them. Okay, so that is you know, that is one kind of relates like solving the PDE to like this perspective of like an eigenvalue, eigenvector problem. Is that making sense? Okay, so now in the remaining minutes, so there is a way to rewrite the wave equation, but I'll probably do it next time. There is a way to rewrite the wave equation using like a Hamiltonian. So that's kind of like nice. It's kind of like an infinite dimensional version of like what we have been doing before. But for that, we have to do like say a little bit you know, about like what a functional derivative is. So let me tell you a bit of that, like how to take derivatives with respect to functions. So I'll just do the two basic examples because that's all that we need. So, okay, so just to recap what we have had so far, we had like a vector, like an infinite dimensional vector space, right? And then, so one of the things we have been considering are operators, right? So one thing that we have been doing is like operators or linear transformations, right? I should call them because like that, because that's what we have been doing. So that's just like, you know, like those are like linear maps of B to itself, right? The other thing that's kind of like useful to consider in general, right, is not transformations from the you know, not transformations from the vector space to itself, but just like maps from the vector space into the real numbers. So let me just see if I want to what type of name for that I want to give. Another thing which you can also like, that's usually what's called like a functional. So I'll call it S, just to not be super biased. So it's something that takes vectors and gives you real numbers. Okay, so in finite dimensions, like what are some, like, you know, in finite dimensions, right? Like A could, like, you know, like examples of, the first case is just like A, kind of like an n by n matrix, right? That's the most easy thing, right? And an example of something like S would be kind of like, for example, like the determine, well, no, you need something that takes like a vector, like, like the easiest thing that you could do here is like, well, one thing, to produce a number out of a vector, like in this case would be, for example, like you could take its norm squared. That would be something that you could get, like, that gives you a number. Another thing you could do, like, on a vector to produce a number. If you have, a matrix, if you're given like a matrix, would be kind of like the quadratic form associated to the matrix, so something like A, B dot A, B. Right, that would also give you a number. So like a few options, like that you have seen like in linear algebra that would, take a vector and give you like a number. Now, for something like what we have been studying, right? Let's say you have like let's continue thinking about functions. You know. So let's say our V, again, just like it's like our periodic function, V F smooth and periodic, right? So here's, so like f of pi equals negative f of pi. So here's, so an example of the operator was a derivative, was an example of something that would give a number out of a function. The easiest thing to create a number out of a function is to integrate it, right? So that's the easiest example, here. So one, let's call it, well, that's not the best thing, but, like one way to create like a number would just be to, I know you see the 1/2 is convenient. You integrate that, like for example, it's kind of like similar to the norm squared like case, like you just integrate the square of the function. And another example, would be something like, instead of integrating the square of the function, you can integrate the first derivative square. So like just to kind of give a little bit more of a geometric meaning, like if you wanted to write this like on R3, so that it looks more like a multivariable calculus thing. Like this is like what I would write as the norm of the gradient of f squared. Right, it does look more elegant that way, but because we're working with functions of one variable, you can just rewrite it this way. So these are just two ways of producing a number. So far, so good. So you have these two operate like transformations or like functionals, take functions and produce numbers, right? So one thing that you could try to take, one would like to make is kind of take a derivative of s, right? So what's like the derivative of s? So how can you take the derivative? How can you take a derivative of s? Right? Because like notice that the domain itself is functions, right? So you're taking a derivative, like it is a bit more complicated because like the domain is not like R2 or R3, right? It's like this space of functions. So let's just start working like with an analogy. And I'll just do these two examples to show you what I mean. So here's again, so again, like any of these is going from. It's going from V into R, right? Just to, again, it's convenient to think about first like in multivariable, what happens. So in multivariable, what would, like, if you thought about V as being R3, right? That's a good example. So you have like a map from R3 into R, right? So what is one thing like, so it's kind of like a function, like a real value function S of X, Y, Z, right? That's how you could think about it. So like, so it's like a scalar field, that's what I'm trying to say. So this was like a scalar field. So what was a type of derivative that you had for scalar fields here? Well, you had the directional derivative, for example. So the one thing that you could do here is like take a directional derivative of the function S, right? In the direction of a vector V, and what you show in multivariable is that that's kind of the dot product between the gradient of the function and the vector, right? Is that okay? Is that making sense? But just to make it more kind of close to what we want to do, let me just rewrite it using this, dot product notation, like the inner product notation. So you could think of like, so like the directional derivative is like a dot product between like something that depends on the vector on f. Sorry, I should have put s here. So oops, I meant s and all of this. So like the directional derivative of s is like something that involves the inner product between the gradient and the vector, but in a sense, like the gradient is like the derivative of the function, right? Like if you think about it. So what is the nice thing about of this perspective of the directional derivative, that the directional derivative did have like this limit definition, which is as what well, I should have put like something like if you think about it as R plus dv minus s of what r is here like x y z over over h, right? So that was like the limit definition of the directional derivative, right? So the thing is that you can kind of like still try to like do like a similar directional derivative definition for something like this. So you can kind of try to compute like the directional derivative of a thing of this sort. Okay, so like let's just think about that. So I'll try to work out like in the remaining minutes like an example of how this looks like for this thing. So let's take the first one. So I want to do something like a directional derivative in the direction of a vector, which I'll call, like the thing is like the vectors here are functions, right? So I'll call the vector v tilde, f tilde. We kind of like to mean like another function. So, okay. This can be confusing. So like, it's kind of useful to like run it again on your heads like later on. But it's kind of like the derivative of this thing in the direction of the function f tilde. Okay, so if you just follow the directional derivative definition, okay, that's what this would be. But what is this? So this would be like the limit as h goes to 0. What is s1 of f plus t f tilde, sorry, this should have been h. Plus h t f tilde is just like integrating the square, so you put like 1/2. Well, there's a 1/2 everywhere, so let me just put like, take out 1/2 out. Okay, so that's what you get from the first case, because it's just squaring the function. And then I'll, like, this one gives you this. Is that making sense? Kind of. Like, so I'm comparing the values of this thing at f and f plus h f tilde. So that's kind of like the analog of s at r and s of r plus, I should have put h here, sorry, hv. Okay. Now what happens here? Like, okay, this is like you should, you can like square this like with the like binomial formula, whatever. So like the f squares cancel out, you know. It's very similar to how you would find derivatives for like x, like x goes to x squared in calc 1. Like, so when you square this, you get f squared plus 2 h f tilde plus h squared f tilde squared, right? So you're integrating this, but you're subtracting it from this integral. So when you subtract this integral, this term goes away, right? You're taking a limit with respect to h, right? So like you divide it by h, and like this will go away as well, like in the limit, because you're taking the limit as h goes to 0. So the only thing that survives, and then there's like 1/2 that kills this too. So what I'm trying to say is that after taking the limit, the only thing that you get remaining is something like this. Like it's just this mixed term, like f tilde. Then we can just, but that, okay, it is useful to kind of try to compare this with this definition. This is like the inner product between f and f tilde, right? So what that means, okay, this will look weird, but like I promise, like it will look less weird like in a second. So okay, so what let's just put it here, sorry. So what that means by comparison, right? I said that like the directional derivative is kind of like the inner product between kind of like a gradient and the vector, right? The vector is this, right? So you want to say kind of like that the derivative, you want to say that you want to say kind of the derivative. So the derivative of S1 at the point F should be just like F by comparison, that you see. Which is the analog? Okay, so this looks odd, but you should compare this with like, with f of x equals 1/2 of x squared, right? It's kind of essentially what we have, like it's like what we have is kind of like the integration analog of this function. And in this case, like the derivative of s1 at x is just x, right? So it's kind of like the same, like it's just saying that the gradient or the derivative of s1 at the point f is just f itself. Because this is really like the version, like, this is kind of like 1/2 of x squared. It's just 1/2 of f squared, but f squared is kind of like the integration. Isn't that weird? Like, I mean, it does take some time to get used to it. It's it's a tricky thing to perform, but like it does like behave more or less like, it is the closest thing that you could ask for, like, if you compare it to like the Calc 1 definition of derivative. It's just that here, this is like derivative along with respect to functions, right? So like there are like different names that you give to this in the literature. This is called like a functional derivative because you're differentiating with respect to functions. But it does like work very close to what we like. It is more or less the thing that I just did. Let's do this for the other one because the other one, and I'll finish with this. So let me do the same for this case because this one is a bit more tricky. So because this one is harder to kind of like get the answer. Like the first one is a bit better to understand it, but okay. So S2 of f is 1/2 of the derivative of the integral of the derivative of f squared. So actually for this calculation, it's actually a bit better to just start with the notation for the inner product. So because you're integrating the derivative with itself, that's 1/2 of the derivative of the inner product of the derivative of x, derivative of f, right? Like because like what that's essentially what this is. And let's see. And I'll even do this a bit better because this is 1/2. So this is like dxf dxf. Okay. So let's keep that like that. And then what we want to do is kind of find the directional derivative of S2 at the point F in the direction of this vector, which I'm calling F tilde. So you do the same as the limit definition of S2 F plus H F tilde minus S2 of F over H. Okay. And what is this? So this is minus it close to 0. Okay, there's a 1/2 everywhere as before. So you get the derivative with respect to x of f plus h f tilde, derivative with respect to x of f plus h f tilde. Okay, that is the first factor. That's what this gives you. Minus this factor, which is just dxf over h. And like, because the derivative is linear, maybe I should just like write it a bit more convenient. So I'll rewrite this as dxf plus h dxf tilde, and then dxf plus h dxf tilde. Okay. So that's what that derivative, that's like what the ratio looks like, the directional derivative looks like. And then how can you do this? Like, like the inner product is bilinear. So you get like this with this, which gets canceled by that, right? And then you get this with this, then this with this, and the other two, right, have like an h squared. When they have an h squared, when you divide by h in the limit, that will go away. So the only thing that survives after canceling by h, and because you get like twice the factor, like the same factor, you get something like, dxf with dxf tilde. Okay, that's actually what ends up surviving. Because again, like the inner product is like symmetric. So, and then you remember, like, you can move this to the other side as a transpose. Okay. And that's just minus the derivative squared. So just by comparing all of these, like, again, we're trying to compare with the fact that the derivative at a vector of f of like a function s2 at r is like the gradient of r times like the dot product between the gradient and the vector v. So if you compare that, like again, like this is kind of matches this. So what that means is kind of like that the gradient in this case should be kind of weird, but the gradient is minus the second derivative. So isn't that like, which is confusing because like you think of the gradient as being first derivative, so that's why you have to be careful. The thing, okay, like I'll explain why this is not created and it looks like. The thing is like this functional already involves a derivative, right? So you're taking the derivative of something that involves already like a derivative. That's why you expect to get like a second derivative in the formula, if you know what I mean. Whereas here, there were no derivatives involved. And so, there like it just drops, like the derivative does behave more like closely how, how in the traditional sense it works. But here, like, since like this is already inherently like something that depends on the derivative, it's not as crazy to think that the formula, would involve the second derivative with respect to x. But it's not something like, like there's some like rules that you can do for like this functional derivatives, but at least these are like the only two that we will need for what follows like next time. So it's kind of like nice to do the calculation to kind of get like a sense of how all these things work in practice. But yeah, like what we just did is kind of like an example of like differentiating a functional like in infinite dimensions. Okay, so like sometimes people will also write this like with a partial derivative notation, but that can be a little bit more confusing. Better to keep it like, in this way. Is that making sense? Okay, let's finish here. So next time I'll tell you how the wave equation kind of can be reinterpreted in terms of like Hamilton's equations, which is very cool. And that kind of puts us more or less that's like the last class that I'll use before telling you how everything looks in quantum mechanics. So like, but we're almost done in terms of like all the preliminary stuff, but it's just kind of like, now we have built almost the entire bridge for that. Okay, so yeah, I'll see you next Wednesday, if that sounds good.